Hello and welcome back to the Astro Imaging channel. Tonight's session is on Understanding MTF, an overview for amateur astronomers, and it's going to be presented by John Hayes. But as always, before we go into that, I'm going to share my screen so you can see this week's image of the week. And I believe you see it. Stop me if you don't. This image, M20 and M8, what is that? The Laguna and the Trifid Nebula. And the winner is George Varoufakis. And as always, George, if you would like to come on to talk about your image next week, just drop me a message, whether it be on Google Plus or go onto our website and find a link at the contact form, and I'll get you an invite to the session next week so you can talk about it a bit. Otherwise, just send me a small message and I'll read it out to people on the air. But oh, and you know, there's one other thing I wanted to say, and I don't know. Let me pull my screen back. I don't know how many people had heard this, but we lost a great astronomer last week, Per Freeval, who had presented for us in the past, and he's actually the developer of Model Maker. If you have a 10 micron mount, you've probably heard of him because he was really a stand-up guy, a developer, and he died unexpectedly. So I just wanted to say that there's some posts in Cloudy Nights if you wanted to kind of pay respects or whatever it may be. Yeah, it's kind of a surprise, and I just wanted to say I should have had something formal written out, but I just wanted to say a couple words about that. So, Per, thanks for all you've done. Rest in peace. Okay, so without any further ado, I am going to pass it over to John, and John is in the room. John, you there?
I am here, Adam, and let's see if we can get the screen share going here. Just bear with me here for just a second, and we'll see if we can get this up. Should be sharing the screen here, and you should see that screen. Do you see Understanding the MTF on the screen there?
Yes, I do.
And it should go full screen there. Does that look good?
It hasn't gone to full screen, so try to make sure you're sharing your full screen or desktop, whatever it says for you.
Let me just see here. We have this trouble every time I come on. So when it says full share screen, it just says share screen. Are there any other options there?
Are you playing your slideshow yet, or are you on your notes page only?
Yeah, I'm back to yeah. I just see share screen here. So it just says share screen. Let's try this. Desktop. Try that.
Start your PowerPoint.
And yes, it should be there, right there.
That's the right one.
And you should see that, and you should see full screen there.
Yep, we're all good.
Excellent, excellent. Well, good. I'm glad you guys are interested in this. This is a topic that, as you know from Cloudy Nights, I like talking about. And I thought, you know, it's a good thing to kind of understand where this stuff comes from, what it means, and it's not a totally trivial topic. I'm going to do my best to give you guys a little bit of understanding of this, and to give you a little background on MTF. And as you guys know, the modulation transfer function is a function that describes how sinusoidal image components are modulated through an optical system as a function of spatial frequency. And this is only for a spatially incoherent extended object, and we'll talk about that as we go through this. MTF is very sensitive to optical quality and to the aperture shape, and it's a very common and useful measure of image quality. And there are other ones, and we're going to talk a little bit about how MTF relates to these other measures of image quality as well, because as you'll see as we go through this, they're all interconnected. But to be useful, you really need to understand what the MTF is. And I have to tell you, this is a big subject, so I'm going to warn you guys. Hopefully I'm not going to put you to sleep, but I got to give you a little bit of background to better understand this, about where it comes from, what it measures, and what it doesn't measure, and what it means. And I'll tell you something, this subject comes about at the end of a Fourier optics, 2-semester Fourier optics graduate level course. So I'm going to be careful here not to get too deep into this, but you're going to see a little math, but I'm going to try to keep it as simple as I can. So in an image, one of the things that I want to just start out and make sure we're all on the same page, and I think a lot of you guys understand this, but a lot of folks come from a background of audio or electronics where we think about frequencies in the time domain. The image domain, we talk about spatial frequencies, and we talk about intensity patterns that have a frequency and a wavelength in space. The spatial wavelength is the distance between adjacent peaks, and I'll show you a picture in just a minute. It has units of length, for example, millimeters, and it has a spatial frequency, which is always the inverse of the wavelength. It has units of inverse wavelength, and we either say inverse millimeters or cycles per millimeter is usually the way we talk about spatial frequency. It also has a direction, so it's expressed in degrees, and again, I'll show you that in a minute. And finally, a sinusoidal image pattern has a maximum and minimum image values. And that's where contrast comes from. And you guys are pretty familiar with contrast, but we'll make sure we have a good definition of that. And these sinusoidal signals, it turns out, are really useful for constructing different kinds of images. And we'll see why in just a little while as we work through this. But just to expand on this whole idea of sinusoidal images, we have to talk about sinusoidal images in 2 dimensions. And on the left there, I've shown a long wavelength, low spatial frequency sinusoidal pattern. In blue there, it shows the wavelength from crest to crest, and it shows it has a direction on the page. Short wavelength, high spatial frequency, of course, the fringes get closer together. And I love to talk about these as fringes because, as you guys may know, I worked in interferometry for a long time, so my life was consumed by generating these kinds of fringes. And in 2 dimensions, we don't talk about just a sine or a cosine. We have to write an expression that is always positive, because in the imaging world, we can't have negative values. So an expression for a sinusoidal image is shown below, where it's just equal to some normalizing value, we call it I naught, of 1 plus this thing called gamma times the cosine of the signal in both directions. It's called a separable function, so we can just multiply one by the other. And it turns out that gamma quantity is the contrast. And the contrast is just equal to the difference of the maximum intensity and the minimum intensity divided by the sum of the intensities. And there's some different ways to define contrast. This is typically the way it's defined for a cosinusoidal image. Sometimes it's been called the Michelson contrast, but I just call it contrast. And you guys are image processors, so you know what high contrast looks like and below what low contrast looks like. And if you were to do a plot, as I've shown there, it shows the minimum and the maximum values and how you would go about calculating the contrast. And before we can really talk about what is MTF, we need to go through a little bit of optics background. And so you got to bear with me here as I talk about how optical systems work. And optical systems, it turns out, they act like low bandpass filters in terms of spatial frequency. So not all spatial frequencies are transmitted equally through your telescope. Some spatial frequencies are not transmitted at all. Okay, and to understand this, we need to look at the wave nature of light and how images are formed. So I got to back up a little bit. In fact, we're going to back up to the 1600s for just a minute and tell you where some of this stuff came from. And this whole field of talking about imaging using diffraction is called physical optics. And so whenever you hear me talking about physical optics or mentioning that on cloudy nights, that's what I'm talking about. It's the whole idea of modeling imaging using diffraction. So let's go back and we'll review a couple of basics. First of all, when we talk about interference and diffraction, that all comes from the fact that light exhibits both wave-like properties and particle-like properties. We mostly use waves or particle-like trajectories to design optical systems and to sort of estimate image quality. That's what we do when we're using an optical design program. But it's the wave properties that best describe image formation and image quality for real-world systems, and that's particularly true for very high-quality optical systems. And of course, we all have very high-quality telescopes, and so it's pretty important to use diffraction and to use the wave-like properties of light to describe how our telescopes form images. And one little tidbit here that I thought is a good thing to mention is the difference between interference and diffraction. They both describe wave interactions in the system. In general, interference describes the interaction between a discrete combination of waves, like 2 or 10 or something like that, whereas diffraction usually describes how light propagates by combining an infinite number of waves. And that's the important one. That's the one that we're going to use to talk about how our optical systems form images. But it's important to understand they're really the same thing. Interference and diffraction are exactly the same thing. And I told you we were going to back up to the 1600s. Here it is. It was Christian Huygens who, back in the 1600s, first developed the theory of wave propagation that's still the basis of modern diffraction theory. He was a very clever guy, and he came up with this really interesting model, and he showed that wave propagation could be explained by treating each point on a wave as a new source radiating a spherical wave at the same frequency and phase as the parent wave. And that all sounded pretty good, but he had to introduce one little tweak to that idea, and that is he introduced, and this was very important, something called an inclination factor, which prevented backward propagation. So with this little inclination factor that he introduced, the light will only propagate forward, but it also can propagate kind of to the sides as well, and almost backwards. And Huygens' idea was the first to explain how light interacts with edges and apertures. And as we'll see, that's very important for understanding what MTF is all about. The whole idea here, and maybe this diagram's a little bit hard to see, but hopefully you can see it well enough to understand there's a point source there on the left. And it's monochromatic. It's just one wavelength, and it's emitting. It's kind of a hypothetical perfect point that's emitting a perfectly spherical wave. And up in that little inset there, you can see the whole idea is that you start with one wave, and at each point on that one wave, a new spherical wave propagates out. And if we add up an infinite number of those things, we can generate a new wave. And by using that inclination factor, adding them all up, integrating them to any direction, we can propagate that wave to any different position on the right. And the cool thing about this is that Huygens came up with this because people back in the even the 1600s could see that at edges there was this ringing phenomena. And Huygens' idea explained that ringing phenomena pretty well. He couldn't really work it out. It turned out he needed more powerful math to really formulate a general solution. But his idea was so good that it's held on all this time, for over 400 years, that this idea is held. And it's been greatly refined. And about 100 years later, after Huygens, Joseph Fourier came along and developed the mathematics of combining and analyzing sinusoidal waves. And this whole theme of sinusoidal waves in images and in Fourier theory, you're going to hear this over and over. That's why the sinusoidal image is so important. The Fourier theory is the computational basis for solving what Huygens' principle turned into, which is the Rayleigh-Sommerfeld diffraction equation. And I didn't write that down. That's a big, complicated thing. But we don't need to know what the equation is, but to understand that it describes light propagation with the interaction of any kind of aperture. And it formalizes Huygens' principle. And it can be solved computationally in the near field. The near field is called the Fresnel field. The far field approximation, though, is the one that makes it very easy to solve the diffraction equation for distant sources. And that's what we typically use in astronomical optics, and this is called the Fraunhofer region. And so when you hear us talking about Fraunhofer diffraction, that's what we're talking about. And it turns out the Rayleigh-Sommerfeld diffraction equation is actually pretty complicated, and when you make some simplifying assumptions, that's what gets you out to the far field. And by the way, the focus of a lens or the focus of a mirror is in the far field diffraction region of an optical system. one of the things that, well, the main thing that Fourier did is he showed that any function can be decomposed into an infinite sum of sinusoidal waves. The sinusoidal waves have to have the appropriate amplitude and phase components, and those components form the spectrum of the function that you're decomposing. And this whole field that's called Fourier optics uses Fourier space, or frequency domain, to simplify the analysis of complex systems. And you guys, if you have never had this stuff, you're going to be saying, geez, this sounds really complicated. And it's a fair amount of math, but it's not. It's actually simpler than you think. It actually makes things a lot easier. And MTF comes from this whole idea of Fourier optical analysis. So we are getting there. And I'm going to have to tell you a little bit about Fourier optics so you can understand where MTF really comes from. And once you understand that, we'll look at simple ways to calculate it and that sort of thing. But again, it's a big subject, and you know, I'm sort of bypassing a whole semester's worth of Fourier optics to tell you guys this. So you're going to have to take my word for a bunch of what we're about to discuss. And I'm going to throw a little math at you, but don't get too frightened. I'll try to explain it in a simple way and mostly bleep over it. But we'll try to look at the Fourier construction of a simple function, and one of the most interesting functions is a square wave. And what I've done here is I've created what's called a discrete Fourier transform of the square wave, so that this little function that I've shown here is the actual Fourier transform of the square wave. And it just turns out to be a sequence. And I just did this in Excel. I just added up the terms of the infinite series. And the first 6 terms are shown in blue. And you can see it's kind of wiggly. If you don't include, the takeaway here is if you don't include a lot of the terms, you get things that are pretty wiggly. If we start including more terms, like the first 20 terms, you can see that the wiggliness starts to go away. It gets a lot more square wave-like. Now, in the case of a square wave, the square wave does have a big discontinuity. Those big steep sides are hard to reproduce. It takes lots of frequency components in order to make those steep sides. So those steep sides, it's important to understand you need lots of frequency components to create steep sides. Why is that important? Well, if we want to look at a steep edge in an image, we need lots of frequency components. So that's an important thing. Now, you'll also notice one other little thing, and that is all that ringing around the edges. That ringing is actually a very interesting historical thing. It was discovered long before the guy it's named after. The guy that's named after is this guy named Gibbs, who figured it out. It's called Gibbs phenomena. He figured it out about, I don't know, 50 years after another guy figured it out, but nobody paid attention to the first guy. It was Gibbs that waved his arms hard enough to make everybody pay attention. And he discovered this little ringing phenomena. And the only way to get rid of that is to have an infinite number of terms. That ringing phenomena will stay there as you add up a finite number of terms. And what happens, it never really goes away. It just becomes infinitely thin. And there's some other mathematical oddities about that. But don't focus on that ringing as much as the fact that as you add more terms, you see things sharper. That's the thing. That's the takeaway from that diagram. And the spectrum of that diagram, if we were to say what's the spectrum of the square wave, well, it looks like this. And this is, I didn't plot this out using any significant units here. I wasn't careful. I want to just state I wasn't careful to make sure this was the same spectrum for that square wave. But this is what the spectrum looks like. It has positive and negative components. It goes to infinity, and that's what the transform of a square wave actually looks like. So we're getting there, and believe it or not, I've got to talk about point spread functions, which is the PSF. So in order to get to the MTF, we actually have to kind of wade through a whole bunch of stuff, and one of them is the point spread function. And point spread function is the system response to a perfect point source. And these have different names throughout different disciplines. Those of you who studied physics will recognize these as eigenfunctions. I never knew what eigenfunctions were when I was an undergraduate studying physics. It wasn't until I got to optics that it made sense that you had a point spread function. So if we take our telescope and we point it at a star is sufficiently distant that in space they act as optically perfect point source. And so, for example, if we got rid of the atmosphere, if we were out where Hubble is and we pointed our telescope at a star, that star image is the point spread function for your optical system. The point spread function, it turns out, is wavelength dependent, and it includes the effects of both aperture and the optical aberrations. So if you have optical aberrations in your optical system, it will show up in the point spread function. And I'll point out that a system, an optical system where the point spread function doesn't vary over the field, that's called a shift invariant system. Not very many of our telescopes are perfect over the whole field. And so what we instead do is we say we'll define this little region called an isoplanatic patch. And that's our little region where the PSF remains essentially unchanged. So kind of right near the middle of the field, we'll figure out what the point spread function looks like. And if we wanted to move off to the sides, we might have to define a different point spread function to see what the MTF looks like off to other sides, other areas, and what the optical performance is. But understand that there is a region around which things change slowly enough that we can say, well, that's close enough. We can determine the optical performance over this part of the field. How is the PSF related to the pupil? The pupil is the optical system. So be careful here. When I use these optical terms, it's basically the exit pupil of your telescope. The PSF, it turns out, and again, I told you I'm going to gloss over a lot of stuff. I'm just going to tell you the fact here is that the PSF is the power spectrum of the exit pupil. In other words, the power spectrum, this comes from the Fresnel diffraction equation, by the way. And again, it's too complicated to go through the math here. I mean, we'd spend pages and pages, and you wouldn't get much out of it. But just take my word for it, that the PSF is the image of the point source, and with a narrow bandwidth, this first equation, the PSF, is what that says is it's the square of the absolute value of the two-dimensional Fourier transform of something that t of xy is just the pupil function. The pupil function is just the next equation is just the pupil shape, that t0 of xy, times the pupil aberration, which is a complex value. It's e to the phi of x and y. And phi of x and y is an optical phase. And that optical phase is just the aberrations in the system. And I know that looks complicated. Don't freak out about it. We'll just accept that. But remember, the takeaway is to remember that the pupil is connected to the point spread function. You guys all know that. I mean, if your system has aberration in it, the image of the star isn't going to be as good. And that's really mathematically what that's saying. And I'll also mention that t of xy is exactly what we measure with an interferometer. We measure the complex pupil function. And that's what we do when we see fringes. But we'll come back to that later and
John?
just mention. Yes.
Josh is asking, what is considered a narrow bandwidth? And actually, before you answer that, I do want to remind everyone Q&A is active, so if you want to ask your questions, just type them in. But yeah, what is considered a narrow bandwidth?
Absolutely. That's a good question. A narrow bandwidth would be something that is basically one color but is not laser-like. So a laser has a spatial coherence that's measured in kilometers. So it is very much a single wavelength. A narrow bandwidth might be something that has a frequency range of, say, 5 nanometers, 10 nanometers or so. Laser light has a frequency bandwidth that's measured in hundreds of nanometers. I mean, or thousands of nanometers. It's very, very. A laser is a very, very single wavelength device. So this is just none of our narrowband filters are monochromatic. Those are all narrow wavelengths. I hope that answers the question. Let's go on and talk about how are images formed in the spatial domain. The spatial domain is where we live, in X and Y. And again, we're talking about an object that's extended, spatially incoherent source, like a cow. And so the object is something that has an intensity distribution of O of xy. We have an optical system that has some point spread function, PSF of xy, and it forms an image of f of xy. And it turns out that the way we form the image is we take the object distribution and we convolve it with the point spread function. Now the convolution process is shown below. It's this double integral. And basically you take the object, you multiply it by the PSF as you shift things around in space, and you form this image that will be slightly blurred. And you guys use convolution in image processing, and you know that convolution is ultimately a blurring process. So the image really cannot ever be as sharp as the object for any real-world PSF. So that's one takeaway here that's important. You can actually prove that an image can never be as sharp as the object. Well, how do we do this in the Fourier domain if we were to work in the frequency domain instead? And this is kind of a cool thing, that we can do imaging in either the forward domain, which is x and y, or we could work in frequencies. Well, it turns out that if we take our object and take the transform of the object, so we convert it into the spectrum, which is a complex number, and then we take and we have something called the optical transfer function. And this is really important. This optical transfer function is the property of the optical system, and it's a property of the optical system. And it turns out if we just simply multiply the spectrum of the object times the optical transfer function, we get the image spectrum of the image, which again is a complex number. We inverse transform that and we get back to the image. And you might go, well, why in the world would you go to all that trouble? Well, it turns out that computationally the transform, the Fourier transform on a computer is much faster than the convolution process. So for a big object, for lots and lots of pixels, you can do this calculation much more quickly if you're doing this as a digital process. So we often calculate images this way just to go faster. Now, of course, we have such fast computers these days, it almost doesn't matter. But we can really speed things up considerably if we go into the frequency domain. Well, what is the OTF? Okay, hang on to your boots here. We said that the image is just equal to the object convolved with the PSF. But if we go into frequency domain and we take the transform of the image, that just turns out to be the transform of the object convolved with the PSF. But one of the rules in the transform domain is that that is just the spectrum of the object times the spectrum of the PSF. So therefore, the optical transfer function has to be just equal to the spectrum, the transform of the PSF. So that's an important thing. So in words, forget that little equation there. Well, you don't have to forget it, but that may be hard to digest. But in words, the optical transform is just the Fourier transform of the point spread function. Remember, the point spread function is just a star. That's all it is, star image. So this is one way to find the optical transfer function. The optical transfer function is a complex number. It has a real and imaginary part. And the real part of the optical transfer function is the MTF. We finally got there. The imaginary part of the optical transfer function is called the phase transfer function. And that tells you how optical phase is shifted. And I'll show you a picture of optical phase in just a minute. So we'll get back to that. But I want to mention that to compute the OTF, it is much faster to compute it in the Fourier domain than it is to compute it in the forward domain. However, it's much easier to understand how the MTF is computed in normal space using pictures. So let's just look at how the OTF is related to the pupil. And boy, this is starting to get really deep because there's so much math behind this, and unless you have some background here, you're just going to have to take my word for this, that the OTF is equal to some constant times the pupil function cross-correlated with the complex conjugate of the pupil function. You have to do a little bit of a coordinate shift there. And that k factor is just a normalizing factor. So it's the same thing at the origin. And we have to do that with the OTF because the OTF is defined to be 1 at the origin. And I'll tell you why that is in just a minute. The autocorrelation is very, very similar to a convolution. It's very similar. In a convolution, we slide one function over another and take the area, but we actually flip one function and then slide it. In the autocorrelation, we don't flip it. Intuitively, it's a little hard to understand what that is, and it looks complicated, but it's easy to understand using a picture. So, I don't expect you guys to fully digest that slide. I want you to know that. But I just wanted to tell you where it comes from so that you understand how the MTF, where the MTF comes from in autocorrelation. And along the top, what I've shown is, let's take a circular pupil, like perfect, and it's perfect. So let's take our hypothetical perfect pupil, and we're going to take, remember what it said to take and autocorrelate the pupil with its complex conjugate. So we're going to take the pupil, lay it on top of itself, find the area of that, and divide that by itself, and that forms the first point on the left there for the zero spatial frequency, and it has to be 1. Well, why does it have to be 1? Well, that's the position, we'll talk about this again in a minute, but that's the position where we have zero spatial frequency. Zero spatial frequency is just the DC component. That's on or off. That's black or white in optics terms. So in any optical system, we can't put in some level of intensity and expect to get out more intensity, just conservation of energy. So we expect, and in this case, by the way, we're ignoring the fact that we might have some transmission losses. So we're assuming here that in this particular system, there are no transmission losses. This is a perfectly transmitting system, just for simplicity. I know that's not real, but for simplicity, bear with me. But we normalize everything for a contrast of 1 at frequency 0. Then we take and we slide the pupil function apart a little bit, find the area again. Again, I'm on the top. I'm sort of on the second from the left on the top. That red area shows what we get at that spatial frequency. We slide it further apart, and you can see the area goes down, and at the end, finally the two circles separate, and we go to 0 at a normalized spatial frequency of 1. Now you can understand why an obscured system doesn't have the same MTF as a unobscured system using this diagram, and I put it on here because it's so cool to see it. If we have an obscured pupil down at the bottom on the left, you can see we take the pupil function, we lay it on top of itself, we divide it by itself, we get 1, and then we start sliding them apart and finding the area under the curve. And you can see that the area under the curve on the bottom there, that red area, is far less than the red area on the top. So the MTF for the obscured system has got to be less than it is for the unobscured system. And you'll notice that that condition continues until we get to the point where the two pupils are, the obscuration is no longer a part of the area. And you can see that when we take that area on the bottom right, it's the same as it is on the other side, but we're divided by lower area. And so it turns out that the MTF for an obscured system is a little bit higher than it is for an unobscured system for high spatial frequencies. And it becomes obvious when you look at this method of calculating the MTF, how that works and why you get an improvement in contrast transfer at high spatial frequencies when you have an obscured system relative to an unobscured system. Now the thing to remember here is that I've only slid this along the x-axis. In order to calculate the full MTF, you've got to slide in all directions in the 2D plane. And if you do that, you end up with a three-dimensional function. You don't often see MTF displayed as a 3D function, and I'm going to tell you why that is. But this happens to be an MTF that I calculated for coma. And it turns out that if you go through the derivation of the PSF, it turns out it's mathematically something called Hermitian, which means that it's odd with respect to its conjugate. So the MTF, it turns out, is mathematically an even function. That means everything on the positive side is equal to it's the same value as it is on the negative side. And because of that, if you look here, you'll see I've taken just a top view of the MTF. And if we take slices through that MTF, you can see that really, if you want to kind of gauge the performance of a system, we really don't have to look at that full 3D plot. I mean, that full 3D plot's kind of hard to digest. Instead, we just take slices, two-dimensional slices. And typically, they're done at 0, plus and minus 45 degrees, and 90 degrees. And right below here, I've shown a plot for coma. And you can see here that there are just 3 slices, and that's because the slices in the plus and minus 45 degree direction for the particular sample I used here. I actually cheated because I was having trouble with the graphics. this plot isn't the same as for the 2D plot up there. It's a little bit different aberration, but don't get hung up on that. But you'll typically see in a MTF plot slices through different directions. And so I think Canon used, I don't know if they still do it, but Canon used to supply MTFs, little piece of paper with the MTF for their photographic lenses. And they always show these these four different slices on their MTFs. And that's why. So what is MTF really telling us? It's telling us that if we have some spatial frequency that we put into the system along the bottom, and it can be high, medium, or low frequency, it tells us how the frequency comes back out the system. And even for a perfect circular system, you can see the contrast gets changed. We don't always transmit the same contrast no matter what frequency. The contrast rolls off up to some maximum value, and then it goes to 0. Okay? So that should be pretty clear. And let's talk about the normalization. Let me go back to that for just a second. We often see MTFs printed out this way, showing MTF 0 to 1 and normalized spatial frequency going 0 to 1. Well, why do we do that? Well, they often do that because we don't really know the optical parameters that went into creating that curve, but we know that the curve is the same for every circular aperture if it's perfect. And so we often normalize the spatial frequency. So I'm going to tell you how to denormalize it. So first of all, let's start, before I do that, let's just start on the left side. And I think I mentioned to you that the maximum the MTF is by definition 1. You know, that's DC, spatial, that's either on or off, black or white. That's it. The curve, the red line, is always the curve for a circle. And you notice that it's not perfectly straight. If we had a perfect rectangular aperture, it would be straight, but there'd be some other problems that we would have. But we normally don't have rectangular apertures, so we won't spend much time talking about that. The important thing is how to decode the normalized spatial frequency. And so down at the bottom right, I've showed what the normalized spatial frequency is. It's 1 over lambda f, where f is the focal ratio, and that's in the focal plane, or it's d over lambda, where d is the diameter of the telescope over the wavelength, and that's in inverse radians in angle space. So that's out in object space. That's out in front of your telescope. And that normalized spatial frequency at 1 is called the cutoff frequency. That's the band limit for the system. You can't transmit any spatial frequency higher than that. And I put the formula there if anybody wants to use it for the two circles there that are for a circular aperture. So you could, if you want to plot it yourself. So why is there a cutoff frequency? That's actually kind of easy to answer. If we have a focal plane, in the focal plane, the F number of the system limits the maximum angle which beams can interfere. Okay, so for larger angles, they interfere to produce more tightly spaced fringes, which are at a higher spatial frequency. So if you look at this diagram on the right, or either one of them, what I've drawn are just the crests of two interfering wavefronts. And at a small angle, you can see they interfere to produce more broadly spaced fringes, whereas at a larger angle, the fringe spacing gets closer together. So it's the F number of the system that determines the fringe spacing, the maximum fringe spacing you can have. And if you go back up here and you look, well, sure enough, in the focal plane, it's only F number that determines that maximum frequency. If you project back out into space, it turns out you got to get the diameter involved, and I won't go through all that, but you can work that out yourself. So in the focal plane, yes?
Josh is asking, why don't we have rectangular apertures?
Well, we do sometimes have rectangular apertures. In various optical systems, there are rectangular apertures. But in astronomy, we usually deal with circular apertures because they're easier to make. So typically, to make a square aperture, we start with a circular aperture and we cut it down. Or we put some apodizing aperture in front of it. And so when we make a telescope, we don't really like cutting up all that wonderful glass we made. And there's really no advantage to having a square aperture. It doesn't really help you. It's much harder to make. There are a million reasons why square apertures are really no good for astronomy. You can have them for some things. Don't get me wrong. There are systems. I can't think of one off the top of my head where you would see a circular aperture, but they have been made, and you can use them. I hope that answers your question, Josh.
His other comment is less wasted image circle.
That's right. Yeah. Well, again, to make a square aperture, you start with a big circular aperture and you cut it down, and you're just throwing away light when you do that.
Yeah.
There's one other thing: the diffraction pattern gets really ugly for a square aperture. You definitely wouldn't like that. You could try that as an experiment, and you can put a square aperture in front of your telescope and see what you get. And I can guarantee you won't like it, unless you love spider. If you like spider diffraction patterns, you'll love a square aperture because that's what you'll get. So scaling. So I thought I'd just give you an example. Again, in the focal plane for a given wavelength, only f number determines the cutoff frequency. So an 80 millimeter f5 and an 8 meter f5 system have the same cutoff frequency in the focal plane. Oh my gosh, I mean, that's kind of startling. So for example, in f10, the cutoff frequency is about 200 cycles per millimeter at a half nanometer or a half micron wavelength. For f2, the cutoff's 1,000 cycles per millimeter. Okay, so obviously, the higher the f number, the higher the spatial frequency gets through. Remember, it's those beam angles. In object space, we got to project back out in front of the telescope, and it's only the diameter that counts. And of course, I love to use my C14 as an example, and I use that. The cutoff frequency there is 3.44 cycles per arc second at 500 nanometers. And that compares to the Rayleigh resolution limit of about 0.35 arc seconds. They're kind of similar. If you take 1 over 3.44, that's kind of close. And of course, for Adam, I had to put in the C8 or an 8-inch. At that diameter, the cutoff goes to 1.97 cycles per arc second. So that's what you get through in that system. And how does that relate to what we see in the sky? Just to give you a picture, I kind of trolled around AstroBin and without permission copied an image that I saw there that was just beyond spectacular. But hopefully the owner will let me use it for this quick presentation. But just to show, Mars, this was taken at the 2014 opposition. So Mars in this case was 15 seconds across. And if you do the calculation, how many spatial frequencies get through, gosh, it's actually quite a few. From that 16 scope, it goes between the blue line and the end. Those spatial frequencies go into making up that 15.1 arc second image. So on pretty big objects, we're using pretty much that whole curve. Just for grins, I kind of calculated you get almost 60 of the maximum cycle across 3.94 cycles per arc second. Of course, the contrast there is 0. But that whole range of components adds to form that image. So I just wanted to emphasize, that curve really goes into forming the images that we see even on pretty tiny objects.
John,
remember, yes?
Cliff is asking, I'm not sure I understand his question, whether he's just asking for clarification as to what cycles per millimeter are and line pairs per millimeter, or whether he's asking about is that the question, Cliff? Yes, clarification on that.
Yeah, so remember when we talked about all the way in the beginning, we had those pictures of those sinusoidal curves. And so, the sinusoidal images. And remember, those sinusoidal images had a peak-to-peak wavelength. So spatial frequency is the inverse of that wavelength. So if the wavelength was 1 millimeter, the frequency would be 1 cycle per millimeter. That would be the frequency. I picked an easy one because I can do that in my head. Obviously, if we had 2 per millimeter, then the 2 cycles per millimeter would be a wavelength of a half. wave per half a millimeter would be the wavelength. Okay, and so when we go back out into space, this is the number of cosinusoidal images we can have in an arc second. Okay, that's the most we can fit in there, and of course the contrast is 0. That's the cutoff. We don't really even see that. It's very, very high frequency. So the wiggles are coming at very, very high frequency, but they're almost 0 contrast here. So we have to back off a little bit before we can even see it. And I want you to remember that MTF only provides part of the story. Remember, it's the real part of the optical transfer function. It only shows how contrast is transmitted. It doesn't show you how optical phase is transmitted. And optical phase is sort of the position of those sinusoidal images. And whenever phase reverses, the MTF has to touch 0, and that's because MTF is always has to be a positive number, and you can never produce a negative contrast. And defocus is a good example. And I took my cell phone out, and I got on my computer, and I quickly made a radial grating using my drawing program. And I just went out and took a picture with my cell phone, and I had to muck around a little bit to get it to go out of focus. But you can see here where the MTF goes to 0. And if you look very carefully at that image, this is kind of a fun image to look at, you'll see that the dark lines go to 0 contrast and emerge as white lines. And you'll see that. That's what we mean by a phase shift. That's when a white line becomes a dark line. And so that is where the MTF goes to 0 at that particular spatial frequency. And if you study this image, it's kind of fun. You can see 1, 2, and actually 3 phase reversals in this image as you move toward the center, and you can see where the cutoff frequency is for that amount of optical defocus in my cell phone. So you see a couple of interesting things here. You can see how the MTF is changing. You can see the contrast getting worse and worse toward the middle of that image. Finally goes to 0 there where it turns gray. The black part is where the lines all came together. That's basically, that's not really a high spatial frequency. That's actually a very low spatial frequency because my printer couldn't print them very well. It turned out to be a black dot in the middle. But where it grays out completely, that's where the MTF goes to 0. And as you can see, as you move toward the outside on the left, the contrast gets better and better the lower the spatial frequency gets. And you can see the phase shift here, which is wonderful. It shows how a black line becomes a white line. So that shows the effect of both MTF decrease and the phase transfer function going through a phase reversal for an image. And all of those components have to add up to make that image. One of the cool things about MTF is that you can cascade MTFs. And they can be cascaded through multiple spatially incoherent coupled image locations. Well, what does that mean? Well, that means if you take an optical system on the left there, it's a lens, and it images onto a diffuse screen, that's the green screen, at an image plane, and then we re-image that using another optical system back to a detector, that the total MTF will just be the MTF of the first system times the MTF of the second system times the MTF of the detector. And that's right, detectors can have an MTF as well. And an example of this would be an SLR camera with a focusing screen. If you wanted to know how good is the imaging through your viewfinder and your DLSR, this would be a way to do it. You could measure the MTF of that lens you screw on the front. You could measure the MTF of the imaging lens and just multiply them together. You can't do that in every case, though. You got to be careful. If the multiple systems are coherently coupled, in other words, there's not a diffuse screen in between things, you can't do that. And so you have to calculate the MTF for the whole thing. So for example, if we're into, say, planetary imaging and we want to do eyepiece projection onto a detector, we have to find the MTF of both the primary of the telescope, the front end of the telescope, as well as the eyepiece that you're using to do the projection back onto the detector. So you got to remember, even looking through the system, that the eyepiece and even your eye are all part of the optical system when you use the telescope visually. So you have to be a little careful and understand, we all know this, everybody sees a little bit different looking through the telescope, and that's because our eyeballs are all different. So we have different MTF response through this, looking through the system when we do this. let's talk a little bit about diffraction limits, because I want to talk very quickly about how MTF relates to diffraction limited systems. And the diffraction limited system is one where the image quality is determined primarily by the properties of light rather than by optical aberration. That's really what a diffraction limited system says. And that implies that the optical aberration is small. And the question is always, well, how small is small? Well, in the late 1800s, physicist Lord Rayleigh, who was a very brilliant guy, I think his name was Johann Strutt or Jonathan Strutt or something, he developed a famous estimate. And his estimate, he said, well, if the maximum wavefront error is greater than about a quarter wave, maximum error, the optical performance will become noticeably different from a theoretically perfect system. So he used third-order spherical aberration to develop this, but his rule applies well to it turns out, almost any combination of aberrations. Now, you can get into a lot of argument, and I see it on cloudy nights all the time, people saying, oh, I can see an 8th wave, I can see a 10th wave. Well, maybe you can. Maybe there are some people who have real eagle eyes, but in general, this is a very well-accepted limit, is this quarter wave limit. And most of our telescopes are made to about a quarter wave. I've measured a lot of celestron telescopes, and even the telescope that I use for a lot of my imaging, it's only about a quarter wave. Maybe it's the wavefront that comes out the back end. It might be a little bit better, maybe a 1/5 of a wave or so. But that's really all you need, and it turns out that gives very, very good performance. And again, I'm talking about the wavefront error, not the surface errors on the mirrors. That's a little bit different. And the Rayleigh rule agrees really well with the requirement that the Strel be greater than 0.8 for diffraction limited performance. That's another sort of accepted figure performance. And Mahajan's approximation can be used to show that the RMS should be less, the RMS of the wavefront error should be less than about a 1/13 of a wave, or 0.077 waves, as a diffraction limit. So we've got three things. We've got sort of the peak to valley error, it's a quarter wave, the Strel greater than 0.8, and the RMS error should be less than about 0.077 waves for a diffraction limited system. Well, how does that translate into MTF? So what I've done here is I've shown you an MTF of the blue line on top, which is a perfect system, and the other three lines are for, one of them's for a quarter wave of third order spherical, the other one, the green line, is for a quarter wave of focus error, and the sort of aqua line there, cyan line, that's one wave of third order spherical balanced against focus, and that turns out to also meet the diffraction limit. So you'll notice that those depart a little bit from the diffraction limited line, and I see endless arguments about this on cloudy nights, that this is a disaster if anything departs from the perfect circular aperture, but that's not really true. I mean, you got to remember, people tend to think, gee, if it departs, I can see that easily. But I hope what I've given you is a little bit of a sense that what you're doing is you're adding up all of these spatial frequency components to form the image itself. It's not, you don't really observe these components directly. You observe the effect of having these lowered components, these slightly different amplitudes that go into forming the image. So you don't really necessarily look directly at this unless you're looking at sinusoidal images. And, excuse me, we usually don't look at sinusoidal images, okay? And by the way, all of these three aberrations here that I've shown have a Strel greater than 0.8. And by the way, I should also point out that a lot of times it's easy to get a quarter wave of defocus in your system. You know, thermal effects and that sort of thing can defocus your system. So focus is a very important aberration to pay attention to while you're imaging. How about for obscured systems? We showed how that's sort of graphically computed for an obscured system. And just for fun, I plotted it out from 0 to 50%. You can see at 50%, which is sort of the, I don't know, that tan brown line at the bottom, gets pretty bad. And it turns out you can do a little calculation. We'll show you this. I'll show you. Well, the result of it is that if the obscuration is about 32.5%, the equivalent Strel of an obscured system will be diffraction limited. It will be greater than 0.8. And so here I've shown kind of 30% obscuration, and you can see, you know, 30%, 32.85, somewhere in there. that's actually, a pretty decent size. That's roughly a third of the aperture being obscured. And of course, it is going to change the contrast of some of these components a little bit. And I do believe that you can see it. But it's really not an enormous effect. And in fact, many of the large, fast astrographs, mirrored astrographs, have obscurations of 50% and a few even larger. Some of these Italian systems are really huge. And you can still get wonderful performance out of these things. Obviously, below about a normalized spatial frequency of about 0.6, the obscuration works to decrease this transmitted contrast. And that's because the outer rings of the Airy disk are sort of enhanced. They get brightened. And that tends to have an effect on lower spatial frequencies. But above 0.6, the obscuration works to increase the transmitted contrast. And that happens because the central peak of the PSF is narrower. And there's what the PSFs look like. Remember, the MTF and PSF are very closely linked. One's just the transform of the other. And so for a perfect unobscured system on the right, you see a nice airy pattern. And by the way, I've really enhanced these faint lobes a lot in plotting this. For a perfect obscured system, 32.5%, and when I say perfect, I mean no aberration, you see that those outer rings are brightened quite a bit. And if it's an unobscured system with about a quarter wave of third-order spherical, again, you can see, and this is not balanced with, by the way, this is not balanced with focus at all. This is just a quarter wave of pure Seidel third-order spherical aberration. You can see the outer rings are enhanced, and that's what causes those lower spatial frequencies when you do the convolution to kind of get blurred out. And again, this was the 32%. I think we've kind of talked about that. Just showing how at 32% the obscuration is pretty much the same. I would argue it's actually better than the Rayleigh limit, just because you get an enhancement, over 40% or so of the curve. One thing I do want to point out, Josh asked about how narrow is narrow. We really have to worry about the fact that the PSF, really, we don't work on narrowband PSFs unless we're doing narrowband imaging all the time. And so a broadband PSF scales with wavelength, and when you do that, it's a little bit of a complicated calculation. I didn't really have the tools to do it, so just to show you what the difference between the PSF and the polychromatic PSF, I just did it in one dimension, and you kind of see the blue line is the polychromatic PSF, and it kind of smooths out the PSF a little bit. And so when you take the transform of the polychromatic PSF, it's going to give you a little bit different MTF. And again, I didn't quite have the tools to do an easy calculation on that to show you what the difference is, but it will be different a little bit when you're looking at broadband stuff. Everybody argues about the narrowband stuff, and it's good for illustrative purposes, but it's not the real thing. One of the things I wanted to do is just to reiterate the connection between all this stuff. We talk about MTF, but MTF's it's all connected. And if we start up in the upper left with T of xy, that's the complex pupil function. That's what we measure with an interferometer. That gives you the pupil aberrations. It gives you peak to valley, RMS, the geometric Strel. That gives you sort of the optical quality. And if you take the convolution, the autocorrelation of that function with its complex conjugate, you get the OTF. And the OTF, the optical transfer function over there on the right, upper right, gives you the MTF. It also gives you the PSF. I didn't write it there. Or the PTF. We normally don't look too much at the PTF. It's really hard to interpret that. But the MTF is, as we've said, is very useful for looking at how frequency components are transmitted. And then if we go into frequency space, which is below the blue arrows, the PSF, of course, is related directly to the OSF. And the PSF gives you optical resolution. It gives you the diffraction Strel and circled energy and those kinds of things. So all these things are really related, which is kind of cool. So it's important to understand that MTF just isn't something that sits out there all by itself. It's related to the point spread function, and it's related to the pupil aberrations of your telescope. Let's talk about what MTF doesn't show you. It doesn't show you image contrast reduction due to stray light, due to poor baffling or reflections, or scattered light due to poor optical surface finish. So if you've got a really, really, really dirty system, or it's not finished well, or there's a problem with the coating, it won't show you any of that stuff. excuse me. And a direct measurement of the MTF doesn't allow working backwards to get the OTF. Remember, you need the PTF to reconstruct the OTF. So any information about what's wrong with your system is lost. So that's important to understand. And when you measure something with an interferometer and you calculate the MTF, you can look at the MTF and say, that's no good, I don't like it, and go back to the pupil and see, gee, something's out of alignment. This looks wrong. Whereas an MTF just shows you that there is something wrong. It doesn't show you really what it is. The MTF also, and I've caught folks on cloudy nights doing this, doesn't really tell you much about imaging or resolving stars. Remember, MTF is about imaging spatially incoherent extended objects like planets of the moon. Okay, so a lot of people really get hung up on MTF, but it really only applies to imaging planets, the moon, maybe a little bit of nebula, but that's really not, you know, unless you're looking at really, really fine detail in a nebula, that's really not what we're doing. Stars are spatially coherent point sources, and they're temporally coherent, they're multispectral, and we got to handle that with the PSF, not with the MTF. How do you measure MTF? You know, I've kind of showed you a bunch of curves. You can generate the curves in design programs, but what if you have an optical system? Well, these folks at Opticos have made a living for a long time making MTF measuring systems. They make a lot of them. This happens to be a picture of one of them. These systems typically measure MTF directly using sinusoidal objects like radial gratings. They can, you know, the advantage of this thing is you can cover multiple wavelengths. You can do multiple field positions. You can do all kinds of stuff with them. And some companies, I think, use this technique for sort of pass-fail for certain types of like camera optics and cell phone optics and stuff. I don't know how they really use it, but the real problem with this is you don't know much about what's wrong with the system. If it's not working right, it doesn't tell you what's wrong. So, of course, I was in interferometry, so I'm pretty biased. This is a picture of a 4D, little 4D Acuphys interferometer. Interferometers, of course, directly measure the complex pupil function. And I know that's kind of complicated words, but it measures the shape of the pupil and the aberration. That's what it does. And that's what goes into the complex pupil function. And then we use that, and I've showed you how the MTF is computed from that. So we use that to compute the MTF. So all of these plots that I've showed you, all of that data was generated by the 4D program. So I just have the 4D program, and I just put in the aberrations I want, and I can calculate the MTF for those aberrations. So that's how I get all that stuff. And it's a full diffraction calculation that's done in Fourier space. The disadvantage of the interferometer, of course, is it's single wavelength. It uses a laser. So you don't get a polychromatic MTF. You don't see how things work in white light or any of that stuff, whereas the MTF measuring system can do that easily. But you do get to measure the aberrations directly. And just finally, for fun, we're just about out of time. For fun, here's what a quarter wave of the 6 Zernike looks like. And Zernikes, I'm probably throwing out a can of worms by mentioning Zernikes, but Zernikes are just polynomials that represent optical aberrations that minimize the RMS wavefront error for each of the terms. And so the comas, the Zernike term that includes coma also includes focus and tilt. So it sort of incorporates a bunch of aberrations, but I just thought I'd throw it in there for a quarter wave. And it gets more interesting when you go to a half wave because you get a phase reversal, and you can see the MTF in the 0 direction actually changes phase. So things get pretty bad with coma pretty quickly. So that's why coma is a particularly bad aberration to have in your optical system. All right, I just dragged you guys through a whole lot of stuff. I hope somebody at least is still awake. So I'll stop sharing and take questions if you guys want to.
Well, first of all, a couple comments that I wanted to mention. First of all, Thomas Dickinson, at some point when we were talking about the square apertures, mentioned that his thesis was on apodized square apertures for exoplanet imaging. Since the PSF drops off faster than Airy pattern along the diagonal. So
okay, well, and that's absolutely, I didn't want to get into that, but since we have somebody here who's an expert on that, there are folks who are apodizing pupils to look at for objects closer to bright objects, and you can apodize the pupil with the shape and with phase masks to handle that. But that's a whole complicated ball of wax. But he's absolutely right.
Oh, I just lost your audio.
Oh, can you hear me now?
Now I can hear you. Yes.
Okay. Okay. I saw a question pop by, but I missed it.
Yes. So actually, okay. So Cliff wanted a clarification. He wanted to know if spatial frequencies measured in line pairs per millimeter are the same as cycles per millimeter.
That's correct. They're exactly the same. The confusing thing when you look at a cosinusoidal pattern is that the peak to peak shows two lines, and so the common terminology is to say line pairs per millimeter. But that's a line pair is one cycle. So it's cycles per millimeter or line pairs per millimeter, exactly the same thing.
Okay. And Josh, let's see. I think it was when you were. I think it might have been before you were talking about polychromatic straw, but isn't that the crux of the matter sometimes, though? The interferometer reading doesn't necessarily show a scope's good performance over a broadband filter. Color correction contrast over a wider RGB filter. Some scopes with 95 scroll ratios don't correct well in color, and then your lume and broadband filters can be blurry. So maybe the limitation of that.
Yeah, that's a big issue. That's a big question. So when you start talking about refractive systems, when you start having the issue of chromatic aberration, an interferometer can miss serious chromatic issues. If you have a full reflecting system, so if you go to your RC, you're going to see the shape of the wavefront at all wavelengths. So that's absolutely correct. You have to be a little bit careful when you're looking at refracting systems to make sure that you don't miss a serious chromatic issue.
Or not so serious.
Or not so serious. Typically, the way manufacturers handle that is they control the radii fairly closely in principle. So for a high-quality system, they typically control the radii and the material content really carefully so that if you can qualify the performance of the system at one wavelength, you're pretty certain you get it right for other wavelengths. But that's not always true. So I'll concede that fact that's absolutely correct. You may have troubles there, and that may be why the MTF system works so well for small camera testing and that sort of thing, because those are refracting systems, and you want to make sure they work at all colors.
Right. I'll speak up more on that. I think that issue did not become as apparent until recently with a lot of the Sony sensors that were hypersensitive in blue compared to a lot of the old sensors, and that's where a lot of the refractors have a much harder time correcting, and so you're not catching that with the strial ratio, which I think a lot of time is taken in the green wavelength and not up into the blue where they have more trouble correcting. But then you can.
I will just say one thing, Josh. In the world of amateur optics, the metrology that's used is very crude, and so I personally take those manufacturer numbers of statements of Strel with a bit of a grain of salt. I want to know how they measured it, because again, Strel is very sensitive to the aberration, and I think when somebody puts out says, oh, here's our system, it's a Strel of 0.97. I'd like to know more about how they made that measurement. And I visited a lot of manufacturers of amateur telescope gear, and the testing capability that I've seen at those manufacturers is very crude. In general, not all of them. In general, a few of them. I mean, the Arcos guys were now out of business. Spent a lot of money. They had a 4D interferometer. I love their systems, but not everybody has that capability. In fact, very few do.
Also, can I follow up with a question then on
Sure.
the corrective optics that most people use? I mean, I think that there are very few systems, unless you're using just a pure RC at native without any kind of flattener or reducer on it, then you're still going to be using some kind of refractive corrector. with almost all systems, right?
Yeah, that's true. I mean, even in an RC system, if you want to correct for the full field, you need a field flattener. So, yeah, that's absolutely right. I think if the system is well designed, the issue of chromatic issues are not so tough. I think where it really becomes tough is when you're trying to design a very high quality apochromatic objective that's designed to cover a very wide field. That's where that's the hard thing. So I think the field correctors can be a problem, but I think the wide field apo objectives are probably, just sort of speaking off the top of my head, I think those are probably the more difficult design issues.
Makes sense with the price of them.
Yeah, well, there's good reason. Those have to be really well made. They're often expensive materials, and you know, and trying to get them well corrected is not easy. Anything?
I'm still having difficulty understanding one thing, and I've heard it before, and it always confuses me. The MTF of an obscured system in high frequencies is actually higher, right? And you went in and explained that a little bit. Higher than a non-obscured system, right?
That's right. That's right. It actually, at the upper end, you actually get better spatial frequency response out of an obscured system than you do out of an unobscured system. Now, of course, that's traded off against the lower frequencies, which are worse. But that means that you get higher contrast at those higher spatial frequencies. You're getting higher contrast transmitted through the system. But still, keep in mind, you know, we don't observe those spatial frequency components, the fundamental components, when we look through the telescope. All of those combine to form the image. In general, when you have more high-frequency spatial components, and I'm going to stick my neck out here. I'll probably get in trouble, but I'm going to say something in general that I think is true. That when you increase those higher spatial frequency components, you're actually getting better edge response than you do with an unobscured system. Those higher spatial frequencies contribute to the sharpness of edges. Okay, but again, you know, that's sort of an intuitive feel for what it's doing. You know, it's hard to this is why I have so much trouble when guys on cloudy nights get on and say, gee, I can see this effect from this particular thing in the MTF. Unless you're looking at sinusoids, it's really hard to tell exactly how does all this add up to form the image that you're seeing. And I think it's often the case that folks confuse scattered light issues with decreases in MTF. The best experiment you can do is to cut out a little piece of paper, put it in front of your telescope, and change the obscuration, because then stray light's pretty much equalized. And you can see a difference, but it's not a huge difference. So, you know, this is a good little experiment, particularly for those who have refractors. You know, use a little bit of, it won't hurt your lens. Just cut out a sticky, you know, one of the 3M Post-it notes, and cut it into a circle, and just kind of tack it right in the middle. It won't hurt anything, and try it, and you can see what the effect of the obscuration is. So, again, kind of sticking my neck out, I'd probably get somebody jump down my throat telling me I'm completely wrong, but I suspect that those higher spatial frequencies that are enhanced actually help a little bit with edge response, if anything.
Hey, John.
Yeah.
What can you help? I think one thing that maybe that wasn't perfectly clear in the presentation is what
Sure.
those higher spatial frequencies represent and what those values represent on your plots there. I think that you said maybe they were normalized from 0 to 1, and up at the higher end where you had the higher spatial frequencies, I think that some of those curves changed around 0.4, 0.5. What do those higher spatial frequencies actually represent?
Well, you mean in terms of numbers? In terms of in terms of numbers?
Sure. Yeah. For example,
let me try, Josh. Let me try one other thing. Let me pull up the screen share again, and let me come back to this, and let me show you a slide that I think may help. So let me just roll back, and let's go back up to, I'm going to go way, way up here. And this is the one I wanted you to remember, which is this one right here. So this is what a square wave looks like when we include mostly the low frequency components. And this is what a square wave looks like when we include a lot more high spatial frequency components. Okay? And so when we're including those high spatial frequencies, and in this case, you know, it goes from a normalized spatial frequency of about 0.6 up, and we have to convert that for your telescope. So when you say, what is that number, we have to know, well, for which telescope. But if we just say, well, from about 0.6 up, we're enhancing those spatial frequencies. And I didn't do that experiment here. I mean, it'd be interesting to just take the higher, you know, maybe 40% of these terms and just amp them up just a little bit to see what does that do to the shape of this whole curve. We could do that. But this is the effect of increasing the frequency content of the system. Okay? So
let me try to clarify the question a little more. And just playing a devil's advocate as if somebody was sitting in a class listening to this, I think maybe it wouldn't be perfectly clear if a higher spatial frequency meant that more light was coming in or that you had a more energetic wavelength coming into your telescope. or what exactly that represents.
Yeah. Well, again, you know, we're talking about contrast. So we're not really talking about the amount of light. We're talking about the contrast content of those spatial frequencies. That's what we're really talking about when we're talking about the MTF response. So, you know, for the increase due to the obscuration, really that, again, I tried to kind of look at that in terms of the PSF. You know, the PSF, if we go back down and see if I can find that real quickly here. If we come back down here, for the obscured system, and it's a little hard to tell, but this central peak is a little bit smaller than for an unobscured system. And that central peak, keep in mind, I've kind of normalized things here to make these lower lobes more visible. Remember, this thing sticks up way above these other outer rings, and that narrower point spread function, central lobe, is what helps you to have a little bit sharper imaging of small features at high spatial frequencies, which means very smaller objects. So I don't know if I'm really answering your question, but if I understand it right, you're really asking what's the effect of those higher spatial frequencies.
To some extent, I think more just in lay terms, what exactly the higher spatial frequencies mean.
Ah, okay. All right. Let's go back up here because I just got to. Oh, well, here it is, right here. So remember, these high spatial frequencies are things that look like this. These are at 0.8. We have really tightly spaced fringes, whereas that's the high spatial frequency content. The low spatial frequency content down here are the variations, the sinusoidal variations in the image that make up the image that are varying very slowly. At the high spatial frequency, they're varying very quickly. Does that help?
I think so. I don't know. I think I was trying to ask that more as a general question for stuff that seemed like it wasn't super clear for the audience.
Yeah, maybe. Well, there's a lot. I've thrown a lot at you guys, so your questions are all good. I've thrown a lot at you here, and remember this: the spatial frequency at the high end, it's being transmitted so that it's coming through at very low contrast. Remember that. So when we talk about the obscured system having a little bit better contrast, it's just what that means is this spatial frequency has a slightly better contrast being transmitted through the system. Now again, we don't observe this. We don't look at an object that looks like this. I don't know if you guys, hopefully you can see my mouse pointer there.
Yes.
But okay, this spatial frequency content here, we don't look at sinusoidal images. Okay, we're looking at craters on the moon, and we're looking at Mars images on Mars, and so that image, remember from Fourier, he tells us that we can combine all of these spatial frequencies in a way to form that image that we see. And the way that it's transmitted is what the MTF is telling us. So it's telling us how much contrast gets transmitted. And then we use that transmitted contrast to combine this to form the image that we see at the output. So this is for a perfect object here, and this is the amount of contrast that we get out for each spatial frequency that makes up the image that we are looking at.
So now I think we're getting closer. So I think maybe the question to make it more direct is, what creates a higher spatial frequency? What kind of object in space?
Good. Image detail. So the more image detail you have, the higher spatial frequency requirements you have in order to see it. So image detail translates directly to higher spatial frequency.
Why?
Okay. And this is this whole concept of Fourier, and I'm going to go back to this thing right here. Here we want to see a good clean edge. Okay? Say we're looking at some feature on the moon that is a trough. Okay? So that it goes down, it goes over, and it comes back up. Okay? If we have only if we only have low frequency spatial content here, we don't see a very good edge there. We see the edge kind of come up in a sloppy way. It kind of looks a little rough, and then it goes back down in a sloppy way. If we add more high frequency components, we get a better edge. We get a better looking edge, and we get a sharper picture of that square wave. Here we've got kind of a blurry picture of the square wave. If I only showed you the first fundamental term, in fact, it would look like a cosine. It would look really blurry. You would hardly even see a square wave.
Right. So
right,
I'm trying to bring this out. So taking it a step further, though, are you getting more terms to create that sharper cliff because the cliff on the moon actually has something sharper, or is it a property of the light that's coming in?
Okay. Well, the image itself is the object is the object. Okay,
right.
It is what it is, and so what we can see in the object is determined by how many, by the collection of spatial frequencies that we can create in the image plane, and that's formed by the F number of the system, or the diameter out. Actually, on the moon, it would be the diameter of the telescope. Okay, so. That's what allows us to gather more spatial frequency content and produce a sharper image. So in general, a smaller diameter telescope will not produce as sharp of an image as a larger diameter telescope, because the larger diameter telescope can produce produce a higher spatial frequency content in the image. Okay, so the more of the spatial frequencies that you have, the sharper the image will be. And it's those high spatial, gathering up all those high spatial frequencies that contributes to having a sharper image. Okay, and that's what I was kind of trying to show you here with this diagram, that if we only include the first 6 terms, those are the low frequencies, the image is kind of wavy and blurry, and by the way, it's ringing. Notice all this ringing. What do you see when when you run the magnification way up? You see lots of ringing at edges, right? There it is. Here, if we throw in more higher frequency terms, we get a better representation of our square wave. Okay, and if I threw in 100 terms, man, this thing would look really good. It would look almost perfect, except for the little bit of ringing at the edges.
Adam, I saw a light go off above your head when that happened. Did that?
Oh, no. Greg Marshall just asked an interesting question.
Okay.
Isn't it true that if you have better high spatial frequencies but poor low frequency, you get better contrast at edges, but they are essentially erroneous, probably appearing as the wrong phase?
Well, yeah. Let's not talk about phase. Phase starts to get really complicated. Let's stick with the statement of low roll off at the low end. Let's come back to one of these here. Whoops. So let's come back to this one right here. So we come back to this one. So when you say roll off at the low end, of course, at DC it has to be 1. You can't ever have an MTF that goes to 0.6. It's always 1. And again, we don't consider issues with transmission. So you could say, well, a solar telescope, it cuts out most of the light, so the MTF's got to start down here. It doesn't work that way. So the contrast of the system is 1 at DC terms. So roll off at the low end here, and maybe a better diagram is the last one with all that coma. Here you go. Here's one with lots of roll off at the low end. So here, yeah, I mean, at the low end, these low spatial frequency, lowered spatial frequency content, all of that contributes to a blurrier image. Now, how that works, I mean, I don't have really a good image for example for what that does, but I do suspect that it will amplify the edges more. And sort of roll off the response of the low frequency stuff. But it's not, the problem with this stuff is it's not really intuitive how the frequencies combine in order to form an image. That's the problem. And that's the problem I always have when people say, hey, I can see that roll off at 0.3. When I look through my telescope, I can see that. Well, I'm not so sure anybody can tell exactly what's doing what, because remember, you're adding up all of these spatial frequencies to form the image itself.
Okay. Now,
go ahead.
I guess my so to kind of summarize what my question was, would the one slide that showed the sinusoidal images or the line pairs, if you take a refractor and you're looking at the high frequency line pairs and you obstruct it, there you may or may not, but theory says you would see slightly better contrast.
Yeah. So yes, exactly. So if you could do an experiment, and whoops, I didn't mean to do that. I pushed the wrong button. So if you could do an experiment, Adam. So if you took, say, and printed out this, okay, you printed out something at fairly high spatial frequency, and you backed up in front of your telescope, and you backed up to where it's right in that range, okay, of angular subtents, where you're at, say, 0.8 normalized spatial frequency. And you could look through your telescope, and what you would see is a low contrast version of this. It would look crummy. You'd see that. And then if you put the obscuration in there, and you could tell that it would increase in contrast. It would get a little bit higher contrast when you put the obscuration in there, as long as you adjust the distance and the spacing right to be at, say, that 0.8 position.
Mm-hmm.
So you could do that experiment. It's a little bit like my cell phone experiment where I showed the phase reversal. So you could do that, and you could see it, but you'd have to, it's a little bit like trying to read a newspaper at a mile. You'd have to walk this thing way out there so that the spatial frequency met the criteria to be at 0.8. If you want to do it, I'll calculate it for you, how far away it has to be, and the whole thing. And then you can put in the circles, and you can see at what point does it obviously make that spatial frequency get considerably higher contrast. So you could do that.
Hey, John, I have a quick question. Is there a real-world example that you could look at an image that's been taken and say this area is high spatial frequency and this area is low? Or are you saying that overall, because it makes up the entire system, you couldn't really tell?
No, you can. I mean, I did one, and I think you saw it. Let's see if I can find it again. I did. This is as real world as it gets. I mean, I did this right out in my office. I took and I made a radial grading here. So this is just a diagram. In fact, I've got it sitting on my desk.
Maybe I just don't understand how that would translate into something like a deep space object, like the horse head, like the clouds.
Yeah. Oh, David. That's where it gets harder. If you talk about, and that's why, again, I have trouble when people say, I can see this component, the effect of this component. Well, probably, maybe you can, but I'm not sure what it looks like. I don't have a good intuitive feel for how those components add up to form the image of the horse head. I don't have a good feel for that. And I will also say that with the obscuration stuff, even if the contrast does get a little bit low in some places, or it affects the contrast of the image, or maybe blurs it a little bit, we have such powerful image processing tools that I don't think it even matters. I mean, I mean, I'll just tell you point blank, I think you can just process it away. So again, I mean, the abstract notion here that I think everybody is struggling with a little bit is this concept that any image can be made up of this combination of sinusoidal components. Okay? And the way you add those up is determined by the spectral content of the image itself. So in other words, we have to take the spectrum, we have to take a sinusoid, we have to multiply it by the spectral amount, and then by how much it's decreased by the optical system, and then add it to all the other ones to form the image. That's basically what we're doing. And so that's conceptually the thing that's a little bit too hard of a leap. I mean, I don't have a good feel. It's like asking somebody to tell you what something looks like in the fourth dimension, maybe a little bit. You know, mentally adding up all of those spatial components to me, I don't know how to do that for something like, say, the horse head or a common image. And that's why I have to simplify it. I had to simplify it with this particular image where I just took a picture of a spoked pattern and showed how the contrast of the spokes changes with the frequency of the spokes and how the phase changes. Okay? So I can understand everybody struggling a little bit with that concept because it is an abstract concept. I mean, that was sort of the brilliance of what Fourier did. I mean, he said, gee, we can decompose this image into all these sines and cosines. And by the way, I hate to confuse you even more, but this is a two-dimensional spectrum. And if you want to look at the spectrum, have any of you played with looking at spectrums in PixInsight?
Yep.
Oh, good. Okay, there you go. So you can take one of your images if you want to see what the spectral content looks like and do the power spectrum, and that shows you the frequency components that are in your image. And if you wanted to do some pixel math, you could actually filter that image to remove some of the terms and then transform it again. Actually, PixInsight doesn't let you go backwards. That's unfortunate. They do.
John, they do have an inverse, right? So yeah, you can do a convolution in the frequency domain by doing first the Fourier transform and then the inverse transform.
Oh, that's awesome. Thanks for telling me that, David. I had only seen the power spectrum. I didn't see that they had an inverse.
Yeah.
Okay. Well, it's really good news. So you could do what's called Fourier filtering, and that's, by the way, what we're talking about. With the telescope, an obscured system or an aberrated system, you're just Fourier filtering the system. So you're taking the spectrum of the. Remember this diagram back. Where was it? Let's see if I can find it for you real quick. What we're doing is it went by. There it is, right there. All we're doing is we're taking the spectrum of the system and we multiply it by some transfer function. Well, you don't have to use the optical transfer function. You could just roll off the middle frequencies and then inverse transform it to get the image. So that's called Fourier filtering. And that's basically what we're doing with the obscured system. We're Fourier filtering the system, the image.
Yeah, so Alex asked something that I'm kind of wondering. Is that decomposition into different frequencies what we do in PixInsight or Registax when we do wavelets?
No. The math behind wavelets is similar in the sense that you have what's called a basis function, an orthogonal basis function. And the orthogonal basis function in Fourier space are these continuous infinite sinusoids. In PixInsight or other programs that use wavelet decomposition, the wavelet looks like basically a truncated sync pattern. So it looks just like, I've got it here. It looks just like this, except it stops right there. It stops right. It goes up, down, and stops right there. So the basis function is completely different when you do wavelet analysis. Okay, and it's wavelet analysis is a very interesting thing that works in a completely different way than Fourier analysis. I mean, operationally. So it shows you it's kind of a different thing than Fourier analysis. It's a really good question, Adam. I should have thought of kind of addressing that, but yeah, the basis is totally different.
It's why you can get similar results but not identical results between using the high-pass function in Photoshop and using multi-scale median transform with a bias to increase, contrast to different structure sizes. You can get something similar but not exactly the same because they're not the same function.
That's exactly right. That's completely correct.
Great.
So I'm going to stop screen share unless that should have stopped it.
Yep.
Okay.
Well, that was a really cool presentation.
There is the pattern. And it's just a piece of paper I printed, and you can see what it looks like. It's kind of fun. So you can try that yourself. You can try. In fact, that's how they measure MTF. You can just take that pattern. This happens to be a square wave. It's not a sinusoidal wave, but you could try it and just see how the contrast changes. Well, we went over a lot of stuff. I threw a lot of stuff at you guys. So you guys all get 4 stars for hanging on, A. And B, I can understand some confusion. I hope I've cleared up at least a few things, at least a few more things that I've added. So there's a lot there and a lot to digest. But I appreciate you guys sitting through this. I know that it's kind of a complicated subject.
No, actually, any presentation that gives me a bunch of questions that I want to research later on is a good presentation.
Okay.
Just like a good article, you have to keep on reading. It sends you on tangents all the time.
Oh, yeah.
Definitely a great presentation. And obviously we went over by a while, so I hope everyone got their questions answered. If not, I'm sure we're going to have John back on to do another one at some point. But thank you, John. Anyone in the room have anything for him? I see some people signing off, and I just want to check Q&A one more time. As it comes up slowly. Greg Marshall is saying, in normal images, most anything other than stars, low spatial frequencies dominate. This is the basis of image compression. Rolling off higher frequencies nicely reduces sharpness, not so much with loss of low frequency response, in his honest opinion. So, okay. Well,
John, one other thing here, John, when you're talking about Fourier transform is composition of sinusoids at multiple frequencies, essentially infinite frequencies, right? Did you correlate that back to what Nyquist was doing for Nyquist sampling? Because it's essentially what you're doing is you're looking at composition of sinusoids, and the highest frequency sinusoid used to compose your signal, whatever that is, that's what you need to sample at 2x, right?
I think we might have lost him. He kind of froze there.
Oh, okay.
He seems locked up. Uh-oh. Maybe he's realizing it now, but
looks like you stumped him, Dave.
He's out.
He had enough.
Well, it's probably opening a can of worms anyway. So
yeah. Well, that was a really cool presentation. Oh man, we're losing lots of people now. I do want to thank everyone for coming on. We will be back next week, where we're some of the usual suspects in the room are going to kind of talk about our systems, what we like, what we don't like, what recent upgrades we've done, and we'll give it from from kind of the point of view of if you don't know anything about imaging systems and you might be buying one, then you'll get something out of it. If you know a lot about imaging systems but you want to know the specifics about a particular system, then you'll also get something out of it. So it won't be one size fits all, but there'll be a lot of informative stuff in there. So I do want to thank you all for coming, and we will see you next week.